In the last class, we have given one tabular form regarding 4-bit case. If we assume all those 4 bits are unsigned category, then we are having one tabular form, the corresponding decimal equivalent. And then if we have treated the binary number, whatever is there in 1's complement form, we have written the corresponding decimal equivalent. Similarly for 2's complement, Sine Magnitude form also, right? So if you observe that particular tabular form, you are having two different representations for +0 and -0. If you see the tabular form which we have discussed in the previous class, for +0 and -0 we are having two different representations in Sine Magnitude form and 1's complement form. We are having two different representations for both +0 and -0 in both Sine Magnitude form and 1's complement form. Full stop. Hence, we never use these two representations while doing arithmetic operations. Because, see, in our daily life, if you see, we will consider both +0 and -0 as 0 itself, right? But if you observe Sine Magnitude form or 1's complement form, we are having two different representations for both +0 and -0. That means it is considering +0 as some other number and -0 as some other number. That's why we never use these two forms while doing arithmetic operations. Okay. If you observe the tabular form for 2's complement form, we are having unique representations. Like 4 zeros is nothing but 0. That means we are having only one representation for both +0 and -0 in 2's complement form. Okay. Next point. We are having same representation for both +0 and -0 in 2's complement form. Hence, we use 2's complement form while doing arithmetic operations. Next one, range of numbers. First, I am considering for unsigned case. For unsigned case, okay, you are having the tabular form for 4-bit case. What is the range? For 4-bit case, what is the range? Just go through the tabular form. You are already having the tabular form. For unsigned case, I am considering for 4-bit case. What is the range of decimal numbers you got? 0 to 15. For unsigned case, all the bits give the magnitude. I am having 4 bits. Okay. With the 4 bits, you can have total 16 combinations of zeros and ones. The equivalent decimal numbers are 0 to 15. Right? This is for 4-bit case. For n-bit case, we can generalize like this. 0 to, this 15 is nothing but 2 power 4 minus 1. 0 to 2 power 4 minus 1. 2 power 4 is 16, minus 1 is nothing but 15. So similarly, here if you observe, I have considered for 4-bit case, here in the power I am getting 4. For n-bit case, it will be 0 to 2 power n minus 1. 0 to 2 power n minus 1. Okay, this is for unsigned category. Next one, Sine Magnitude form. For Sine Magnitude form or 1's complement form, you will get the same range. You will get the same range. Just go through the tabular form for 4-bit case. What is the range? Just go through the tabular form. You can go through either Sine Magnitude column or 1's complement column. For 4-bit case, what is the minimum value? What is the maximum value? Yeah, correct. -7 to +7. Minimum value is negative maximum. -7 to +7. This is for 4-bit case. So this one we can write it as 7, we can write it as 8 minus 1. 8 we can write it as 2 cube minus 1. 8 is nothing but 2 cube. Here I am considering for 4-bit. In the power I am getting 3. So this 3 I can write it as 4 minus 1. Okay. So for 4-bit case I am having the range -7 to +7. So I am just arranging in terms of n. Here for 4-bit case in terms of 4 I am rearranging so that I can write the generalized formula. For n-bit case, the range of numbers that we can represent in Sine Magnitude form or 1's complement form. So here in the place of 4, write n. You will get the generalized case for n-bit case. So for n-bit case, you will get the range as -2 power n minus 1 minus 1 to plus of 2 power n minus 1 minus 1. Minus 2 power n minus 1 minus 1 to plus of 2 power n minus 1 minus 1. See here for 4-bit case I got here 4. For n-bit case just replace wherever 4 is there, replace with n. See, very simple. If you consider all the bits as the, like here unsigned category, all the bits give the magnitude, right? So here if you are having 4 bits, with that we can represent the total values 0 to 2 power 4 minus 1. For n bit case, it is like 0 to 2 power n minus 1, right? So, whereas for sine numbers, we are reserving the MSB for sine bit. If it is 0, which indicates positive number, if it is 1, which indicates negative number, right? So here what we are doing, among n bits, we are reserving 1 bit for sine. So with the help of remaining n minus 1 bits, we can represent the magnitude, right? So here the range for n bit case 0 to 2 power n minus 1. Okay, for positive numbers, so the range will be what? Positive maximum value will be, in the place of n substitute n minus 1, you will get here 2 power n minus 1 minus 1. That is the positive maximum value. Similarly for negative maximum, in the place of n substitute n minus 1, you will get negative of 2 power n minus 1 minus 1. Okay, among n bits, we are reserved 1 bit for sine. With the remaining n minus 1 bits, we are using for magnitude, right? So in the place of n substitute n minus 1, you will get positive maximum. Similarly, you will get negative maximum. Okay, this is for sine magnitude form or 1's complement form. Next one is 2's complement form. For 4-bit case, what is the range you got? Just go through the tabular form. Yeah, minus 8 to plus 7, correct. See here you are having 8 minus 1, but there you are having 8 only. Okay, so that means I no need to subtract 1 from here. So I will get, for n-bit case I am directly writing, here I should not subtract 1. Okay, so you will get minus of 2 power n minus 1. 2 plus of, here plus 7 you are having. So for n-bit case, generalized case, whatever the value here you got, I am copying as this. See, for sine magnitude or 1's complement form, negative maximum value we got minus 7. Okay, that one I have written as minus of 8 minus 1. Okay, whereas in 2's complement form, for 4-bit case, we got negative maximum is minus 8. Right? So that means here we should not subtract 1. So for generalized case, n-bit case, here I should not remove 1. That means minus of 2 power n minus 1. Whatever the positive maximum is there, same thing I have copied. Here in 2's complement form, we are getting one negative value extra because we are having same representation for both plus 0 and minus 0 in 2's complement form. We are treating 0 as the normal value, like one value only, like either plus 0 or minus 0. We are having 4 zeros. Suppose for 4-bit case I am talking. Okay, so that's why here we got one negative value extra. Write down the question. The range of signed decimal numbers that can be represented by a 6-bit 1's complement number is. See here, for sine magnitude form or 1's complement form, we are having the same range. Range formula is same. So substitute n value 6 here. You will get the range. Minus 31 to plus 30. See here 1's complement form. 1's complement form is you have to use this particular formula, range formula. Either for sine magnitude or 1's complement, you are having the same range formula. Whereas for 2's complement, you are getting one negative value extra. Next question. Let x be the number of distinct 16-bit integers in 2's complement form. Full stop. Let y be the number of distinct 16-bit integers in sine magnitude form. Full stop. Then x minus y is. Here he has mentioned x is the number of distinct 16-bit integers in 2's complement form, and y is the number of distinct 16-bit integers in sine magnitude form. See, whatever the answer you will get for this particular question, that is the same answer will be valid for any number of bits. It will be valid for any number of bits. Yeah, answer is 1, correct. See here, just observe, for 4-bit case we have considered, for 4-bit case in sine magnitude form, we got the range is what? Minus 7 to plus 7. Minus 7 to plus 7. Range is nothing but what? Maximum value minus minimum value. Right? So plus 7, first I am discussing for 4-bit case. Whatever the answer you will get for 4-bit case, the same answer will be valid for any number of bits. Okay. So for 4-bit case, we got the range is minus 7 to plus 7. That means total number of values, that is nothing but maximum value minus minimum value. From this we will get plus 7 minus of minus 7. That is nothing but plus 14. Or you can say 14 values. Anything is okay. Total number of values is 14, or you can say range is nothing but maximum value minus minimum value. Okay. Similarly here, for 2's complement form. In 2's complement form, here we are having minus 8 to plus 7. So from here you will get plus 15. plus 7 minus of minus 8, that is plus 15. So here in this case he has mentioned x is the number of distinct integers in 2's complement form. Here you assume this is 15. Okay. Here 14. This is nothing but y. Suppose for 4-bit case I am considering. So x minus y is what? 15 minus 14 is 1. So the same answer will get for any number of bits. See here the main important keyword in this particular question is distinct. Distinct integers. See in our daily life we will consider both plus 0 and minus 0 as 0 itself. Right? So if you go through the tabular form for sine magnitude form. Okay, you are having plus 0 to plus 7. Okay. And minus 0 to minus 7 or minus 7 to minus 0. But we will consider both plus 0 and minus 0 as 0 itself. Right? So that means here you are having 0 to 7 or plus 0 to plus 7. You are having 8 numbers. Okay. Similarly, minus 0 to minus 7 or minus 7 to minus 0. But I will consider plus 0 or minus 0 as 0 itself. Distinct integers. See in this particular question, the very important keyword is distinct. Right? So here you have to consider minus 7 to minus 1. So here you are getting 7 only. So that means what? 8 plus 7 is 15. Total distinct integers is 15. See, just go through the tabular form regarding 4-bit case, sine magnitude form. Sine magnitude form. There you are having plus 0 to plus 7. Total 8 numbers. Okay. Similarly, negative numbers you are having minus 0 to minus 7 or minus 7 to minus 0. But in this question he has mentioned distinct. The very important word is distinct. Distinct means you are having different. Right? So here minus 7 to minus 1. So total 7 negative numbers. Total 15 only. Right? Whereas in 2's complement form you are having 0 to 7 positive numbers. You are having 8. Similarly, negative numbers you are having 8. Minus 8 to minus 1. So here you are getting 8 plus 8 is 16. So 16 minus 15 is 1. If it is not distinct, see, if you are having 4-bit case, suppose you are having total 16 combinations of zeros and ones, right? There you are getting 8 positive numbers, 8 negative numbers, either in sine magnitude form or 1's complement or 2's complement form, right? Since he has mentioned distinct, so we have to consider plus 0 and minus 0 as 0 itself, right? So that's why here we are getting one additional integer extra when compared to sine magnitude or 1's complement, right? So in this case we are getting 1 as answer. That 1 is the valid for all the cases, whatever may be the number of bits. Whether it is 4-bit, 8-bit or 16-bit or any number of bits, the same answer you will get. See here we have considered for 4-bit case range, right? Similarly you can frame for 8-bit case. You are already having the range formula, you can substitute. See here previously I have considered range is nothing but maximum value minus minimum value. Similarly you can use this formula, generalized case. Range is nothing but maximum value minus minimum value. So this is as per this context y. Okay. So here also you can do range is nothing but maximum value minus minimum value. From here whatever you are getting, that is y. Okay. So do x minus y. Here in this case n value is 16. You can put n value any number of bits. Okay, you will get the same value. X minus y is nothing but 1. Yeah, here 1 is nothing but 1 integer you are getting extra. See, very simple. For 4-bit case in sine magnitude form. Okay, you are having positive numbers plus 0 to plus 7, 8 numbers. Okay. And similarly minus 7 to minus 1, 7. 8 plus 7 is total 15. 15 integers. For 4-bit case I am talking. So you are having total 15 integers. Okay. In 1's complement form or sine magnitude form. Okay. Whereas for 2's complement form, you are having plus 0 to plus 7. That means 8 positive integers you are having. Similarly, you are having minus 8 to minus 1. That means negative integers also 8 you are having. 8 plus 8 total 16. Here for 4-bit case, if you are having 4 bits, in sine magnitude form you are representing 15 integers, whereas in 2's complement form you are representing 16 integers. So difference of those two is what? 1. Okay, the same thing will applicable for any number of bits. X minus y equal to 1. Is it clear? Next question. 11101, comma 1001 and 11101 correspond to the 2's complement representation of which number? That means here he has given 3 numbers. All these are represented in 2's complement form. Okay, all these 3 numbers representing the same value, right? What is that equivalent number he is asking? See, whenever you are having less number of bits, you can put the positional weights, and since the sign bit is 1, you can put minus in front of that corresponding positional weight. Okay, suppose here 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. Here sign bit is 1, I am placing minus sign. So now add the corresponding positional weights wherever the bit value is 1. So minus 16 plus 8 plus 1. That is nothing but minus 16 plus 8 is minus 8. Minus 8 plus 1 is minus 7. So answer is minus 7. Now let us check whether we are getting the same answer or not. Now here position weight is 2 power 0, 2 power 1, 2 square, 2 cube. Since sign bit is 1, I will put minus here. Minus 8 plus 1. That is nothing but minus 7. Okay. Here position weights are 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4, 2 power 5. Here sign bit is 1, I am placing minus. So minus 32 plus 16 plus 8 plus 1. Minus 32 plus 16 is minus 16. Minus 16 plus 8 plus 1. That is nothing but minus 7. So we are getting the same number, minus 7. So answer is minus 7. Next question. This number when stored using 8 bits will be. Write down the 4 choices. See here you are having a number which is represented with 4 bits in 2's complement form as like this, x3, x2, x1, x0. Now the same number he want to store with 8 bits. So what is the equivalent representation he is asking? See, just for this question you can take the help of the previous question. See here, if you observe, see first I am having 1001, that is like your 4-bit case, x3 to x0. Okay, now here sign bit is 1. Okay, you have placed one more time here. Okay, so the resultant value is same. Here you have placed 2 more times. The resultant value is same, right? So that means for negative number, sign bit is 1, you can place n number of times to the left of that particular sign bit, the equivalent value doesn't change. Similarly for positive number, here MSB will be 0, right? So if you want to represent the same number with more bits, you can place the required number of zeros to the left of this particular sign bit. The equivalent value doesn't change, right? So for generalized case, see, if it is a positive number, we will place zeros to the left of that particular sign bit. If it is negative number, we will place ones to the left of the sign bit. For generalized case, whatever the sign bit you are having here, the same sign bit you can place n number of times. That means option C is the correct answer. The equivalent value doesn't change. Okay, from this particular question, we can get one more conclusion in the reverse way. Suppose he will give some particular number like this. Suppose in terms of zeros and ones, I am talking. Okay, so whenever you are supposed to calculate the equivalent value of this entire number, okay, you can just observe here. This equivalent number is same as what? This number, which is same as this number. That means what? Here the sign bit is 1. If you consider for 4-bit case, here this sign bit is 1. Here I placed one more time. Here I placed 2 more times. That means in the reverse way. Suppose whenever you are supposed to find out the equivalent value of this one, just observe how many times that particular sign bit has been copied. Okay, you can ignore and you consider here. So whatever the equivalent value of this one, 1001, here we got minus 7. The same answer will be valid for whatever the number he has given, right? So that means if you are having the generalized case like this, okay, if you are supposed to find out what is the equivalent value of this entire thing in 2's complement form, I am talking about. Okay, there you just observe here all these 5 bits are what? X3 only. So that means whatever the equivalent value of this entire thing is same as the equivalent value of this one. So like that you can calculate. Okay, now I will give one more question. You use this particular principle. Whenever you are supposed to find out the equivalent value of a particular number which is represented in 2's complement form. Okay, just observe how many times that particular. See here, 1 is placed 3 more times, right? So the equivalent value of this entire thing is same as what? 1001. Write down the question. The 16-bit 2's complement representation of an integer is. He has given the integer like this. He has represented one integer in 2's complement form like this. Full stop. Its decimal representation is. That means you are supposed to find out what is the decimal equivalent of this one. Just observe here. Here you are having sign bit as 1, right? So that same one he has repeated this many number of times. So if you are supposed to find out what is the equivalent of this entire number is same as what? If you find out the equivalent value of here, because see here if you consider this particular number, what is the sign bit here? 1. That indicates that number. Here he has placed simply 1 some number of times. So the equivalent value doesn't change, right? Minus 11 is the correct. Fine. So here 1 0 1 0 1. Just put the position weights 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. Here sign bit is 1. I am placing minus here. So minus 16 plus 4 plus 1. 4 plus 1 is 5. So minus 16 plus 5 is minus 1. Answer is minus 1. Next question. The result of 45 base 10 minus 45 base 16 is expressed in 6-bit 2's complement representation is. See here he has given two numbers, okay, and the resultant value he is expecting in 2's complement form. Okay, so first let us do the subtraction in the decimal. Okay, this is the decimal number, so I am writing as it is 45 base 10 minus. Here here he has given the hexadecimal number. In order to get the equivalent value, you have to put the position weights in powers of 16, right? So here 16 power 0, 16 power 1. 16 4s are 64 plus 5, that is 69. 69 base 10. What is the equivalent value? See, you are subtracting larger from smaller. That is not possible, right? So take minus sign and then subtract smaller from larger. So here 69 base 10 minus 45 base 10. So you will get minus 9 minus 5 is 4, 6 minus 4 is 2. Minus 24 base 10. Now we have to represent minus 24 in 2's complement form with 6 bits. Okay, first let us consider for the 24 for unsigned category. 24 is nothing but 16 plus 8. 16 plus 8 plus 4, 2, 1. Here if you write position weight 2 power 0, 2 power 1, 2 square, 2 cube, 2 power 4. 16 plus 8 is 24. This is for unsigned category. For unsigned category, all the bits give the magnitude. Okay, now I am representing plus 24 in 2's complement form. Here sign bit 0 indicates positive number, remaining bits are the magnitude. Okay, this is plus 24 representation in 2's complement form. Now we want to represent minus 24. Apply 2's complement to this one. From right hand side till you get first time 1, you will copy all the bits. 0, 0, 0. Here I am getting first time 1, so I will copy up to here. From right hand side to left hand side till we get first time 1, we will copy all the bits and then complement remaining bits. 1 becomes 0, 0 becomes 1. That means 1 0 1 0 0. Even if you put position weights, from there also you will get the same answer, minus 24. Here 2 power 0, 2 power 1, 2 square, 2 cube. 2 cube is nothing but 8. Okay, 2 power 4, 2 power 5. Here position weight is 2 power 5. Its sign bit is 1, so I am placing minus here. So minus 32 plus 8. You will get the same answer, minus 24. See, the main advantage of 2's complement technique is, see, suppose you wanted to perform the subtraction a minus b. Okay, actually what you have to do in general, if you are not using 2's complement, you will check which number is greater. Okay, if suppose a is greater, then you will subtract b from a and you will give the positive sign to the resultant value. Suppose if b is greater than a, then you have to subtract a from b. Okay, and then you will give the resultant value sign is nothing but minus, right? So like that we have to compare, okay, which one is greater, which one is smaller, and then to the resultant value we have to put the sign of the larger number. But the advantage of 2's complement technique is, okay, here we will perform the addition only, but only thing, whatever the negative number is there, that negative number we will represent as 2's complement of positive number. Suppose a minus b, okay, this one we can write it as a plus of minus b. Okay, you are having a, another number is minus b. Okay, that minus b I can write it as 2's complement of b. 2's complement of b. That means what? If you are applying 2's complement to positive number, you will get negative number. After that, see here, you are having one number like a, another number is like x. So that means you are adding those two numbers only. But the resultant value what you are getting, that is the a minus b. That is the advantage of 2's complement technique. Here, instead of having two separate hardware circuits, like for performing addition and for performing subtraction, we are having the same hardware circuit, say like binary adder. We will discuss in the upcoming chapters. Okay, the same hardware we can use for subtraction also. That is the beauty of 2's complement technique. Here, actually, we are supposed to perform subtraction. The same thing we are getting. See, we are adding two numbers. One number is a, another number is 2's complement of b. Right? The resultant value here will get a minus b. This is the advantage of 2's complement technique. Instead of having two separate hardware circuits, we can have the same hardware circuit. Okay, for performing both addition and subtraction. If you want to perform addition, then I will take a plus b. Okay, if I want to perform a minus b, then I will take a plus 2's complement of b, like that. So it's like you are adding two numbers only. One is a, another number is b for a plus b. Okay, if you want a minus b, then I will, in the place of b, I will take 2's complement of b. So that positive number will become negative. Okay. Next question. X equal to 0 triple 1 0 and y equal to 1 1 0 0 1 are two 5-bit binary numbers represented in the sum of x and y represented in 2's complement form is within brackets 6 bits. You can write within brackets 6 bits. The sum of x and y represented in 2's complement form within brackets 6 bits. See here, he has given two numbers x and y. Both are represented in 2's complement format. Now here we are supposed to perform x plus y. Okay, and the result he is expecting in 6 bits. Okay, and he has represented in 2's complement format. Okay, now I am considering these two numbers. X is 0 triple 1 0 and y equal to 1 1 0 0 1. Now here our intention is x plus y. That means add these two. 0 plus 1 is 1, 1 plus 0 is 1, here 1, 1 plus 1 is 2, sum is 0, carry is 1. 1 plus 1 is 2, here sum is 0, carry is 1. See, in 2's complement format, we should not consider this carry. Because see here, if you observe, both the numbers are represented in 2's complement format. That means what? Sign bit is, MSB is reserved for sign bit, right? Here MSB is 0, that means it is a positive number, right? Similarly here MSB is 1, that means it is a negative number, right? So that means actually what you are doing, here you are doing apparently like addition, but actually internally going what? Subtraction. See, individually if you are able to represent a particular number 5 bits here, okay, here I have represented one number with 5 bits, another number with 5 bits, okay. Here I am performing subtraction operation. Obviously, the resultant value which you will get will be what? You can accommodate with the same 5 bits. See, whenever you are adding two positive numbers or two negative numbers, that time you will get the overflow. That overflow I will consider. Okay. But here, if the carry is coming, whenever you are performing addition of two numbers, okay, if those two numbers are like one is positive, another one is negative, okay, if I am getting that overflow, I won't consider that is due to overflow. Okay, so I will ignore this particular carry. See here, just write the decimal equivalent of these two. Here sign bit is 0, remaining bits give the magnitude. What is the value? This one I am asking. Plus 14, right? Here sign bit is 1. This entire number is same as this number, right? Here position weight is 2 power 0, 2 power 1, 2 square, 2 cube. 2 cube is nothing but 8. So I will put minus here. Minus 8 plus 1 is minus 7. Actually you are subtracting what? Two numbers, 14 and 7. Okay. So the resultant value is plus 7. So that's why I have ignored this particular carry. Okay. So, but here the question is, we want to represent with 6 bits. So what I will consider? I will place 0 here. Here actually we are doing subtraction. But the advantage of 2's complement technique is just if we add two numbers, from that we will get, see, a plus of minus b. That minus b I am representing as 2's complement of b, like that. So the answer for this question is 0 0 0 1 1. But most of the time in hurry we will choose this one, 1 0 0 1 1. That is there in the option here. Okay, don't do mistake. Whenever we are adding two numbers in 2's complement form, just observe the sign bit. Okay, if those two sign bits are different, that means actually you are performing subtraction. That means if any carry coming, that carry you have to neglect in 2's complement form. Yeah, suppose if we are considering both the numbers in positive or both the numbers are negative, that time if I am getting carry, that carry I will consider. Because see, whenever you are adding two numbers, obviously the resultant value is what? Positive. Similarly, when you are adding two negative numbers, the resultant value is negative, like that. Okay, so there if it is carry is coming, okay, that I will consider. There I will put, suppose if you are adding two positive numbers, okay, though the resultant value that should be positive, so I will put sign bit as 0. If you are adding two negative numbers, okay, then obviously the resultant value is negative. Okay, there I will put, suppose if you are getting, okay, say positive number, there I will put 1 as the MSB, so that the resultant value will be negative, like that. But here we are adding one positive number with a negative number. That means actually you are performing subtraction. The resultant value you can accommodate with the same 5 bits. Here in this case 5 bits we have considered. So that means the resultant value is here plus 7. The same plus 7 we have to represent with 6 bits. So I have placed one more 0. In this way you can solve the problems related to the 2's complement technique. Especially as per gate exam point of view, 2's complement is very important. Okay. So just go through the tabular form. We have discussed for 4-bit case. From that we have given the generalized case, range of numbers. Okay, for generalized case, for n-bit case, unsigned case, sine magnitude, 1's complement, 2's complement, and then we have discussed the problems. Okay.